following video presentation represents Allied Signal's engine's recommendations for the care and feeding of the TPE 331 family of turboprop engines. The information contained in the video represents the best possible balance of performance, cost effectivity, and reliability from these engines. We recognize there are many sources of information available that may affect the decisions that we make as pilots. Perhaps the most important teacher is previous experience. The material contained in this video is based on Allied Signal Engine's previous experience that we gained during the design, testing, and certification of the TPE 331 engine. It also contains information that we have received from you as operators, information that you acquired during the operation of this engine. The information contained in this presentation is, to the very best of our knowledge, fully compliant with the various aircraft flight manuals. It's important, however, to remember that the FAA-approved flight manual is the final authority for the operation of the aircraft and the engine. During this video, we'll review a normal operational cycle. We'll take a look at pre-flight, cockpit setup, normal and abnormal engine start, and abort start procedures. We'll emphasize those areas where we're aware that engine cost or reliability could be adversely affected. The TPE 331 is a single shaft cycle engine, sometimes referred to as a fixed shaft engine. That means the engine compressor and turbine, as well as the gearbox, engine accessories, and the propeller shaft are all integrally connected. Spin the propeller, and you're turning the entire engine and all the engine-driven accessories. In addition to providing essentially instant response to throttle changes, the single shaft engine design can be valuable for other reasons. During pre-flight, for example, you can rotate and listen to every accessory connected to the engine. Listen for unusual noises or higher than normal resistance to rotation. If the engine is hot, within 30 minutes of shutdown, you may notice a slight binding as the engine main shaft rotates through 180 degrees. This phenomena is called thermal distortion and is quite unusual outside the first few hours of operation on a new or overhauled engine. It's caused by a tightening of the engine seals due to thermal expansion. Turn the propeller to the position where resistance feels most obvious. Wait approximately 3 minutes, which is adequate to allow continued cooling to balance the process, and check again. Some amount of free play in the rotational direction is normal. Fore and aft movement potentially indicates unacceptable wear on the propeller shaft thrust bearing and is a grounding condition. As you rotate the propeller, take a look at propeller condition. Nicks or gouges in the prop should be noted for maintenance as they would be on any engine. Look at the spinner and propeller hub for evidence of oil or grease leaks. Improper servicing can cause grease to leak, leading to propeller imbalance. Finally, the propeller should be at the flat pitch or on the locks. If it is feathered, the electric unfeathering pump, with the throttle in the reverse pitch range, will put the propeller back on the start locks. We recommend turning the propeller only in the normal direction of rotation, as reverse rotation can damage the brushes in the starter generator. Because of the centrifugal compressor design, the TPE 331 requires no particle separators or filters. This mesh screen was added by the airframe builder to keep birds and other large objects out of the engine. It's been reported the screen does a pretty good job. The TPE 331 uses an integral inlet designed to be part of the engine. The aircraft manufacturers appreciate this feature as well because it makes engine installation simpler. From an engine perspective, this design feature complements what the engineers call inlet recovery. It allows the engine to take advantage of ram induction. Note any evidence of damage to the inlet surface, including the paint. Bare paint may be treated in accordance with the Aircraft Light Maintenance Manual to avoid corrosion setting in. Looking further back in the inlet area, you'll note the P2-T2 sensor located about 9 o'clock. This device keeps the engine fuel control unit informed about air temperature and pressure in the inlet. Pay particular attention to the small opening in the tip of the P2 mast. This is an area where debris may collect. Check that the board-on tube, which measures air temperature, is intact and free of damage. Finally, look at the face of the first stage compressor impeller. While turning the propeller slowly, inspect all 360 degrees of the first stage impeller for evidence of damage. Any obviously bent or damaged blade should be inspected in more depth in accordance with the engine maintenance manual. Oil levels are best checked after the last flight of the day, while the oil is still near normal operating temperature and is evenly distributed. If you check oil levels after the aircraft has been sitting for several hours, do not add oil until you verified the oil level is actually low. If the oil level indicates low, motor the engine to 10 to 15% RPM without fuel and ignition and check the oil level again when the propeller stops. Motoring allows the oil scavenge pumps to return any oil which is collected in the bottom of the engine gear case to the oil tank, where it can be accurately measured. Remember, modern turbine engines don't consume oil, but oil may be lost in other ways. Oil in the inlet, after the engine has been stationary, could indicate a seeping compressor seal. This is not dangerous, however, if excessive enough, could lead to oil foaming in the oil tank and some loss overboard through the oil tank breather. Likewise, oil in the tailpipe could indicate seeping at the turbine scavenge pump seal. Seepage at this seal is not necessarily dangerous, but if continued seepage is noted, or if seepage becomes excessive, investigate. A complete failure of the turbine scavenge pump seal will result in the rapid loss of engine oil. Maximum oil consumption is 1 quart in 12 hours. Many TPE 331 engines are equipped with an oil bypass indicator mounted adjacent to the filter housing. Take a look to ensure the filter has not become clogged and is bypassing oil. The same is true on some installations of the fuel filter. If so equipped, inspect the fuel filter to ensure it has not bypassed, indicating fuel contamination. Inspect the oil cooler to ensure it is not blocked with dirt or debris. Take a look in the tailpipe area for evidence of damage or excess oil. As mentioned, oil found in the tailpipe could be originating at the turbine scavenge pump seal. Although no limitation is generally published, when possible, position the aircraft in such a way that it is not started in a strong tailwind. If the aircraft is positioned downwind, expect slower acceleration and possibly higher than normal peak turbine temperature during the start. The changes in starting characteristics are due to a combination of propeller loading and exhaust gas re-ingestion. Experience will tell you how much tailwind is acceptable. Monitor downwind starts carefully. After adjusting the seat, rudder pedals, and harness, set the parking brake. Set the emergency fuel cutoff to the normal position. Turn the battery switch on. It's very important to use adequate and properly charged batteries of 24 volts for all engine starts. Consider using an auxiliary power source when ambient air temperature is 10 degrees Fahrenheit or colder. Set the RPM lever to low RPM and the throttle at flight idle. This throttle position ensures propeller blades stay fully on the start locks at minimum aerodynamic drag angle during starting. The engine fuel switch is cycled to off and then placed in the center position. Put the fuel valve in the on position and turn the aux fuel pump on. Fuel pressure should indicate 8 psi minimum. The NTS, or negative torque system, should be tested during the first start of the day. Press the NTS test light to verify the bulb will illuminate. Turn the unfeathering pump and the NTS switch on and check that the NTS light is illuminated. During engine starting, the NTS light should extinguish as the starter is engaged and then re-illuminate as the engine accelerates through about 30% RPM. Place the engine starter switch in the ground position and observe initial propeller rotation. The initial rotation of the engine imposes the largest electrical load on the batteries or the external power supply. A quick glance at the battery voltmeter can tell you how well your electrical system is responding. Consider including this in your cockpit cross-check as sort of an electrical trend analysis. You will typically see a momentary droop in indicated voltage, typically to about 16 volts, followed by a fairly rapid recovery back toward about 20 volts on battery starts. Response will naturally vary under different ambient conditions and with batteries or auxiliary power units of different capability and health. Prior to reaching 10% RPM, place the ignition switch to the on position and note the ignition light is illuminated. At 10 to 12% RPM, after observing the ignition light is on, turn the engine fuel switch on. If you do not have an indication of a rise in turbine temperature by 20% RPM, abort the start. Use the fuel enrichment switch to maintain normal acceleration at an indicated turbine temperature between 650 and 680 degrees on the TPE 331-10 engines. Most pre-century -1, -5, and -6 engines utilize a different internal fuel schedule and will normally not require enrichment other than during the first start of the day. Follow the flight manual recommendations for earlier -1 engines as well as pre-century engines. Do not use enrichment fuel above 700 degrees on -10s or 900 degrees ITT on the -5 and -6 engines. An initial rise in oil pressure should be evident between 20 and 30% RPM. The RPM range between 18 and 28% is an area where the TPE 331 is sensitive to a natural resonance or vibration. Do not allow the engine RPM to dwell or hang in this RPM range. Minimum acceleration should be at least 1% RPM increase per second. If RPM is not increasing normally, abort the start. If the engine stops accelerating or the turbine temperature rises rapidly toward the start limit, abort the start by activating the emergency fuel shutoff lever. Following any aborted starts after the fuel valve was opened, whether a failure to start or a hot start, perform a dry motoring or ventilation run prior to any further start attempts. To ventilate the engine, motor the engine without fuel and ignition to 15% RPM and then allow the propeller to fully stop. The ventilation run clears the engine combustor of unburned fuel and fuel vapor and stabilizes internal engine temperatures. Never re-engage the starter motor while the propeller is still turning. At 72% normal idle RPM, check normal oil pressure is at 40 psi minimum. The starter switch is turned off, the generator switch turned on, and the unfeathering pump and NTS check switches turned off. Prior to start lock removal, a test of the Overspeed fuel governor can be made to verify correct function. The test is recommended following any maintenance involving the engine control system or any indication of a malfunction. This test should be accomplished in a clear area, well away from structures, vehicles, and other aircraft. Ensure the parking brake is set and the wheels are chocked. Set the RPM lever to high RPM. While holding the stick fully aft, slowly advance the power lever toward takeoff until no further increase in RPM is indicated. RPM should stabilize between 103 and 104%. The maximum allowable RPM is 106%. Don't rush this test, but don't remain above 101.5% RPM any longer than necessary to verify correct overspeed fuel governor operation. Before taxi, recheck oil pressure, oil temperature, and applicable warning lights. The beta light will remain on during ground operations. Start lock removal is accomplished by slowly bringing the throttle lever aft toward reverse. A simultaneous rise in RPM, torque, and turbine temperature indicates reverse angle is being achieved and the start lock pins retract centrifugally. Taxi operations are normally conducted at low RPM using brakes and engine thrust for aircraft control. Prior to takeoff on later model EGT-equipped aircraft, set the turbine temperature bug to the correct EGT for the existing indicated outside air temperature. Note all engine instrument indications are normal. Turn the fuel boost and ignition on and advance the RPM lever to high RPM. Verify 96 to 97% RPM is indicated. Advance the throttle while observing both torque and turbine temperature limits. Remember, as airspeed increases, the torque and turbine temp may also increase slightly. During climb, reduce engine power slightly and, if so desired, reduce engine RPM to 97%. Turn ignition off. The fuel pump may also be turned off, provided you are not using aviation gasoline as an alternate fuel. Caution: do not use beta range in flight unless you are certain your aircraft is equipped with a beta propeller control cam. Prior to the final landing approach, select high RPM and turn the fuel boost and, on some aircraft, the ignition on. On EGT-equipped engines, check and reset the EGT bug for takeoff power. After the tail wheel is on the ground, release the flight idle stop and move the throttle aft to ground idle or into reverse as necessary for braking. After clearing the runway, the aux fuel pump may be turned off and the RPM lever reduced to low RPM. Operate the engine for 3 minutes at low RPM and power, including normal taxi time. After engine cooling, place the engine fuel switch in the off position and hold it there for about 5 seconds. Select reverse throttle position at approximately 50% RPM and reposition back to flight idle after the propeller stops rotating. Make a note of engine spool down time for future reference. The information contained in this brief video is intended to generally address all makes and models of Garrett TPE 331 engines currently installed in agricultural aircraft. For specific recommendations, consult the appropriate aircraft flight manual. If you have operational questions about the material you have seen here or the TPE 331 engine family in general, please contact the Allied Signal Engines Pilot Advisor Group at area code 602-231-2474, or if you wish by fax at 602-231-5045. We may also be contacted by mail at the address shown. Thank you. Fly safely.